So far in this chapter, we have been talking about redox reactions, how to recognize them by assigning oxidation numbers, and how to balance them in a couple different ways. Let's now talk about really what one of the main points of the chapter is, which is using these redox reactions or electrochemical reactions to generate energy, and specifically energy in the form of moving electrons that we can use to power some electrically powered process. So let's take a look at a reaction here, and the reaction is the reaction of zinc metal with copper 2 ions to form copper metal plus zinc 2 ion. And so there are a couple pictures here. What happens if you take a strip of zinc and you put it into a solution of copper, in this case it's copper sulfate, copper 2 ions are blue. What happens then is this spontaneous oxidation reduction reactions. Zinc metal gets oxidized to zinc ions. And so what happens on the surface of this piece of metal is that the zinc metal atoms are having 2 electrons removed from them. They're being oxidized to form zinc ions, which go into solution. So that's what's happening over here. The copper ions, which are blue, are gaining 2 electrons from the zinc, and they are plating out on the surface of the zinc. And so blue copper 2 ions are being converted into red copper metal. Silvery colored zinc metal is being oxidized into clear zinc ions or colorless zinc ions. And what you would observe over a period of time eventually was that not only that would you see this sort of copper plating out on the surface of the zinc, but eventually this solution would go from being blue to being colorless because all of the copper ions would have been reduced and replaced by zinc ions, which are colorless. Well, this is a spontaneous process, which, whereas as we learned back in chapter 4 when we were talking about the activity series, the reverse reaction is non-spontaneous. So if I put zinc into a solution of copper ions, I will get a reaction which forms zinc ions plus copper metal. But if I put a piece of copper into a solution of zinc ions, nothing will happen. Well, now in chapter 19, we learned a couple things about spontaneous processes. One is that they increase the entropy of the universe. That's of less concern to us here than the other thing, which is that they release energy. In other words, when a reaction is spontaneous, the value of the free energy of the system goes down, and so the value of delta G is negative. Energy is released, electrons are transferred, those electrons have energy, and so that energy is released. And so we have a system that we can actually take energy from to power something. But the problem with it as it stands now, simply putting a piece of zinc into a solution of copper sulfate, is that all of that electron transfer is occurring right at the surface of the metal. The thing that is being oxidized, which is the zinc, and the thing that is being reduced, which is the copper ions, are in direct contact with each other, and so those electrons are just being transferred right at the surface there. What we would like to be able to do is have those electrons pass through a wire so that we could use that electrical current to power something. And so that is where the concept of the voltaic cell comes in. A voltaic cell is simply a device that allows us to take a redox reaction and run it in such a way that we can generate energy from it in the form of moving electrons. So in order to do that, we use what's called a voltaic cell. And the key to a voltaic cell is that we take the redox reaction and we actually physically separate the 2 half reactions. So in this beaker here, we have a piece of zinc metal immersed in a solution of zinc sulfate. And in this beaker here, we have a piece of copper metal immersed in a solution of copper sulfate. The spontaneous reaction has zinc being oxidized. And so over in this beaker, zinc metal starts to slowly dissolve away from the electrode and becomes zinc ions in solution. Over in this beaker, copper ions in solution begin to plate out onto the copper metal. And electrons are flowing through the external wire because it's the zinc that is being oxidized. It is giving up electrons, which flow through the wire, come over to this side, and are used to reduce the copper ions in solution into copper metal. And I'm actually able to generate a chemical circuit there and a flow of electrons, and it has a measurable voltage, which we'll talk about in a little bit later what that means. So let's look in a little bit more detail at what is going on here. Anyway, again, this is called a voltaic cell. It is doing the exact same reaction that we saw in the previous slide, but instead of doing it in a single location, it is doing it in two physically separate half reaction cells. Okay, so a typical cell is going to look like this. In this cell, in this beaker, just like we saw in the previous slide, I've got an electrode of zinc metal immersed in a solution of zinc sulfate. But sulfate is just a spectator ion, so it's immersed in a solution of zinc 2 ion. In this beaker, I've got a copper electrode immersed in a solution of copper sulfate, but more to the point, in a solution of copper 2 ions. Now, what's happening is, again, zinc is being oxidized. So this is the compartment in which oxidation is occurring. This is the compartment in which reduction is occurring. And simply by convention and definition, we call the oxidation compartment the anode, and we call the reduction compartment the cathode. And there's a very straightforward mnemonic for remembering this. And the mnemonic is this: oxidation occurs at the anode because both oxidation and anode start with vowels. Reduction occurs in the cathode department because both reduction and cathode begin with consonants. So just to summarize again, when the reaction starts, zinc metal gets oxidized to zinc ions. The electrons that are produced by that oxidation are, here's the half reaction. Zinc metal is being turned into zinc ions plus electrons. Those electrons pass through the wire, through the external load, down to the copper electrode. The copper electrode takes those electrons and uses it to reduce copper ions from solution so that they plate out on the surface of the copper electrode here. Now, there's one little problem with the reaction as I've demonstrated it to you, and that is, as soon as electrons start flowing, I'm going to have a charge imbalance because I am generating cations in this compartment, specifically zinc. And so this compartment immediately is going to become positively charged. In this compartment, I'm reducing copper ions. I am taking them out of solution. And so immediately this compartment is going to become negatively charged. It's going to have more sulfates than copper in it. And if that begins to happen, then the reaction will just stop because you can't have solutions that aren't balanced in terms of the total charge of cations and anions within them. And so we add a particular thing called a salt bridge. And the salt bridge is simply sort of an inverted tube here that contains a very highly concentrated solution of something like sodium nitrate. And so because copper ions are being consumed in the cathode compartment, then sodium ions will move out of the salt bridge and into the cathode compartment to replace them and keep the charge in this solution neutral. So for every copper ion that is plated out onto the electrode, which has a charge of +2, 2 sodium ions would have to enter into the cathode compartment here to balance the charge. For every zinc ion that is generated in the anode compartment, I am now generating a +2 charge, and so 2 of these nitrate ions would have to flow into the anode compartment in order to balance out that charge that I'm creating. And by the way, this is how anions and cations actually got their name. Anions are called anions because they migrate toward the anode. Cations are called cations because they migrate toward the cathode. Once again, this is the overall reaction that is occurring. Okay, so we use this salt bridge. I didn't realize I had two slides on the salt bridge, but the point again is that as the reaction proceeds, the charges in both compartments are going to be balanced by having anions migrate into the anode compartment to balance out the zincs that are being created, and having cations migrate into the cathode compartment to substitute for the copper ions that are being consumed. Okay, so therefore, in the cell, electrons, and I was pointing this out in a previous slide, electrons leave the anode compartment because whatever is in the anode compartment is being oxidized, therefore it is generating electrons. They flow through the load, they go to the cathode where they are used to reduce whatever cation is in solution. We showed salt bridges earlier. Another way to have this occur is with a porous barrier. And so, for example, you could just have a porous barrier that allows sulfate ions to move in either direction, but doesn't allow any cations to move. So just ignore this thing that says cations. And so as copper ions are being removed from the cathode department, the sulfate ions that were there could simply migrate across that porous barrier to move into the anode compartment where the zinc ions are being generated. So whether it's a porous barrier or whether it's a salt bridge, you have to have some mechanism by which anions can either migrate from the cathode to the anode or can be placed into the anode from the salt bridge, in which case then cations would be put into the cathode compartment from the salt bridge. And so this is just a further description of what we were just talking about. Electrons leave the anode compartment because the electrode is being oxidized. They make the cathode electrode negatively charged, which then attracts the cations that are in solution here. In this case, it would be copper ions, if we're staying with the same reaction we were talking about before, which get plated out as copper on the copper electrode. So what would a typical problem look like that would be associated with trying to put all this stuff into practice that we've just been talking about? Well, here I have given you a copy of the activity series of metals that we talked about back in chapter 4. Later in this chapter, we'll actually talk about how to use something called a table of reduction potentials rather than the activity series. But for now, I'm going to stick with what you know, which is the activity series. So the first part of this question is simply going to be use the activity series to determine which of the two reactions below is spontaneous. And so this is simply a reaction written in one direction and then the same reaction written in the other direction. Which of these two is the spontaneous direction of this? So if you'd like, you can turn the video off, take a look at the activity series, and then turn it back on. Okay, well, as you recall, for a reaction to be spontaneous, the substance that is being oxidized has to be further up the activity series than the substance that is being reduced. And so if you look at the activity series, nickel is higher on the activity series than copper. Therefore, I want the reaction in which nickel is being oxidized and copper is being reduced. And that's the case in the first reaction. Nickel is being oxidized to nickel 2, copper 2 is being reduced to copper. And so this is the spontaneous reaction. Well, from there, let's go on and see what we can do in terms of an electrochemical cell. Given that we have decided that this is the spontaneous reaction, that nickel reacts with copper 2 to give nickel 2 plus copper 0, go ahead and take this diagram and label it with the locations of these four species: the nickel metal, that is the nickel electrode, the copper electrode, the nickel solution, and the nickel ions in solution and the copper ions in solution. Once you've done that, show the direction of the flow of electrons in the wire, the external circuit that is presented here, and then show the flow of ions both within the anode and cathode compartments and out of the salt bridge. So you can, if you want, just take a minute to pause this, think about what the answer might be, and then turn it back on. And so this is probably going to be the ugliest thing I've shown you all year, besides perhaps pictures of myself drawn by Parker McConnell. But this is the answer to the question from the key to a test that I gave a few years back at Vistamar, of course, where all the wonderful things happen. So the first part of the question asked you to label the locations of the nickel metal, the copper metal, the nickel ions, and the copper ions. Well, because nickel is being oxidized in this reaction, and as you'll recall from our mnemonic, oxidation occurs in the anode compartment, then the nickel metal and the nickel ions are going to be in the anode compartment. The nickel metal is going to be the electrode, and the nickel ions are going to be in solution. The copper metal and the copper ions are going to be in the cathode compartment because copper is being reduced. Reduction occurs at the cathode. So the copper metal is going to be the electrode in the cathode compartment, and the copper ions are being reduced in the cathode compartment. The next thing it asked you to do was show the direction of the electrons moving through the external circuit. Well, electrons always go in a voltaic cell from the anode to the cathode because oxidation is happening at the anode, reduction is happening at the cathode, and so electrons from the oxidation of nickel go through the external wire to feed the reduction of copper ions at the cathode. You can ignore this about voltage. We'll talk about this later in the chapter. Finally, it asked to talk about the movement of ions within the solution as well as from the salt bridge. Well, nickel ions in the solution are going to be moving away from the anode electrode itself because the anode is actually dissolving. Nickel is being oxidized to nickel 2, and those ions are moving away from the anode. In the cathode compartment, copper ions are migrating toward the cathode to get reduced. And then as far as the salt bridge is concerned, anions are migrating out of the salt bridge into the anode compartment to equalize the charges to neutralize the charges on the nickel ions being produced. And cations are migrating into the cathode compartment to replace the copper ions that are being reduced to copper metal. Well, I was going to spend some time talking about electromotive force, but I think that actually gives us everything on this video that I would want to do on a QOD. So the QOD will have to do with just a general understanding of how a cell like this works, the names and locations of various things. And so, things along the line of what we just did, or recognize just matching where do various things occur. And so that's what you can look for in a QOD assignment. Thanks for watching.